All right. So today we're going to be talking about mechanical damping in MEMS. So the first thing that we're going to be talking about is the relationship between the damping and the quality factor of a device. So for any simple mechanical resonator, we know that our force F will be equal to our mass times our acceleration plus our total mechanical damping factor times our velocity plus our spring constant multiplied by our displacement. This is a relationship that you guys should have seen in the lecture related to accelerometers. And in this case, this coefficient gamma here is the total damping coefficient for the system. So damping is defined as the restraining of vibratory motion by the dissipation of energy and therefore it represents energy losses in a system. So in a MEMS device, there are lots of different damping mechanisms that can potentially impact device behavior. So some of these are things like, and we're going to talk about them all in a little bit, so I'm not going to list them out here specifically, but material losses, anchor losses, surface losses, mode conversion losses, air damping, so frictional losses, things like that. Okay. So when multiple loss mechanisms are present, the damping forces of each contribution add together giving us a total damping coefficient of gamma total is going to be equal to gamma 1 plus gamma 2, et cetera, et cetera, et cetera, all the way to some gamma sub n. And the units of our damping coefficient are newtons seconds per meter. A figure of merit commonly used to describe damping in a system is its quality factor. Q, where quality factor Q is simply the ratio of the initial stored energy divided by the energy lost in 1 radian of oscillation. So I'm defining it in this way just for what it's worth. For you electrical types, to get rid of that pesky factor of 2 pi, that's not going to matter for us because we're talking about a mechanical system. But when we talked about it in electrical things, there was a factor of 2 pi that wound up canceling out anyway. And I'm defining it as over 1 radian of oscillation so that we don't have to worry about that pesky factor of 2 pi here in a mechanical system. So essentially, our damping coefficient and our quality factor are inversely proportional to each other, meaning that if we have a high degree of mechanical damping, we'll have a low quality factor and vice versa. So in that sense, we can express our quality factor as omega naught times our mass divided by our damping coefficient, or alternatively, this could be the square root of our spring constant times our mass over our damping coefficient. And this is going to be a unitless or dimensionless quantity. So if we associate each damping mechanism with its own quality factor, we get, so we would have gamma total is gamma 1 plus gamma 2 all the way out to gamma sub n is going to look like the square root of k times m over q1 plus the square root of k times m over q2 all the way out to the square root of k times m over q sub n. There's a common factor of the square root of k times m that we can take out. And so here I'd have 1 over q1 plus 1 over q2 all the way out to 1 over q sub n. And from here, we would then say that gamma total over root km is just the sum of the reciprocals of our quality factor. So essentially, what I'm trying to get out here is that our overall quality factor is going to wind up being smaller than the smallest quality factor associated with any individual damping mechanism. So they essentially combine like resistors in parallel. So if we have one loss mechanism that is dominant, then essentially that smallest quality factor tends to dominate the overall quality factor of the system, where, just for what it's worth, this thing would be 1 over Q total like so. And so now I want to talk our way through some of the various different loss mechanisms that we are going to see. So the first one that I want to talk about is material losses. So material losses are due to movement at the atomic level that results in heat generation. So this is essentially an inherent internal friction, essentially. And it is going to set the fundamental limit for the maximum attainable quality factor. So this is essentially us accounting for thermal noise in our resonator, right? So material losses are going to be dependent on the temperature, vibrational frequency, and amplitude. And the vibrational mode. We'll talk about that in a moment. Of the structure. At room temperature, a simple viscous damping model is appropriate for most MEMS materials. So I'm going to do that on this next page. So let me scroll up here a smidge. So this model is our stress T is equal to Young's modulus times our strain. We've seen this over and over and over again. And now we're going to have another term here. So this is going to be mu gamma, where this is our viscosity measured in Newton seconds per meter squared. And then our viscosity is multiplied by the derivative of our strain with respect to time. And for periodic oscillation, this comes out to be Young's modulus times our strain plus J omega viscosity times strain. So we can see that the elastic damping losses are proportional to the time derivative of the strain. And the damping experience increases with vibrational frequency. Okay, so we are going to define what's called an intrinsic quality factor. And this is effectively just going to be, like I said earlier, the maximum possible quality factor that we could ever achieve. So if our material was perfectly manufactured in a vacuum, et cetera, et cetera, et cetera, this is the cream of the crop thing. Okay. So our intrinsic quality factor due to material losses will be defined as Q sub I. And this is Young's modulus divided by viscosity times the frequency of our oscillations, which could be rewritten as F, our linear frequency, times Qi is equal to Young's modulus divided by 2 pi times our viscosity. And this is a constant value. So the FQ product is a figure of merit that is used to choose low loss materials. For like resonator designs and things like that. Hard materials like, let's see, I have silicon, aluminum nitride, and diamond have large FQ products where this is greater than 10 to the 12, while soft materials like metals and plastics have low FQ products, typically ranging from, 10 to the 8 to 10 to the 10. All right, I'm gonna give you guys a moment to catch up because I don't know about you, but my hand is hurting. I feel like I'm writing a lot really fast. 10 to the 12th power. All right, so now let's talk about anchor losses. So anchor losses, occur when essentially we accidentally transfer some of our vibrational energy into our substrate through our anchors, right? So anchor losses are, oh, I guess I should probably write that down. So anchor losses occur when a non-negligible portion of vibrational energy is transferred to the supports of a microstructure. These losses typically depend on the location of the support point and the type of anchoring that is used. Okay. So this is a difficult thing to specifically determine. So usually computer simulations are used for the modeling the structure as a whole, resonating it at frequencies of interest, and then you effectively back calculate what those anchor losses would actually be. So for a cantilever beam, the anchor losses have been found to be, based on this computer simulations, approximately equal to 2.17 times the ratio of the length of the beam cubed over the thickness of the beam cubed. And that's the only information that I was able to find for any specific type of structure. Okay. So in many applications, including things like accelerometers and actuators and things like that, we don't particularly need a high quality factor because we're just trying to measure a change, not necessarily anything direct. Like we're not intentionally trying to vibrate or anything like that. But if we want a resonator where a high Q is required, essentially, there are different ways that anchor losses can be mitigated, and it's usually based on geometry. Okay. So one pretty common microstructure that is used is a double-ended tuning fork geometry. So let me see. So to cancel / mitigate anchor losses, geometry can often be exploited. So I might have a structure something akin to this, right? So let's say that I have an anchor structure here on one side, and then an anchor structure over here on the opposite side. And instead of having a single beam, I might put two of them. So here's my structure where this guy and this guy are my resonating structures. So essentially, these guys are going to wind up resonating 180 degrees out of phase with each other, such that the stresses from the two resonator arms cancel each other, yielding a net force. Goodness, that looks terrible. Of 0 at the anchor. So this is one thing. Like I said, this is a double ending tooting fork. One structure that we saw, and we actually saw something like this in our last class meeting for the magnetic actuation, would be a longitudinal mode beam resonator. So instead of using torsional beams to cause it to rotate, well, we'll see it in a second. So another way to do something akin to this, where we are going to cancel things out, would be something like that. Yes. So if they vibrate 180 degrees out of phase, meaning when one deflects up, the other one deflects down, the net stress is going to be 0 at our anchor points.
Or that, or by geometric spacing them so that for whatever frequency
I think it's the geometric spacing. Yeah, the physical implementation of the system causes when one goes up, the other one will sympathetically deflect down and vice versa. So, excuse me. Another structure might be something like this. So I've got my two anchors like so. And then I can essentially have a double-ended cantilever structure. This, and if I were, say, piezoelectrically exciting this guy such that it was experiencing extension and contraction like so, well, if we anchor it at exactly half of the total length of the structure, we're going to get essentially no net stress exerted on our anchor itself. So let me put that down here. So anchoring at the nodal point of the resonator where no net stress is exerted on the anchor yields extremely high quality factors as well. That looks like a Q, not a G. This is an example of a longitudinal mode beam resonator. And then here, so we can know which title's going along with which thing. And then the last geometry that's been used in the literature for anchor loss mitigation is what's called a torsional resonator, where essentially this is going to look similar-ish to another structure that we saw in class on Friday. So where we might have something like this. So we're going to have our anchors, let's say here and here. we would have a torsional spring connecting to a frame and then our frame would be connected by a second torsional spring to an interior resonator. Like so. So that essentially our inner resonator is decoupled from the anchor by a second outer resonator. With a low resonant, goodness, I can't. Frequency. So this is, like I said, a torsional resonator, where the outside structure has a low resonant frequency due to its larger mass, and the inside resonator has a very high resonant frequency due to its smaller mass, so that effectively none of the vibrations from the inner resonator can actually propagate to the outer resonator because they're canceled out by that, or none of the vibrational energy can be transferred to the anchor points because it's only going to hit that lower frequency resonator first, which is actually going to get us into mode conversion losses here in a couple of minutes. Anyway. So before we talk about mode conversion losses, let's talk very briefly about surface losses. So essentially surface losses occur due to surface roughness of our structures. These can be caused by contamination, and or oxidation. Typically speaking, the quality factor is measured before and after a heat treatment step. And any reduction in Q is attributed to surface losses. In MEMS, surface losses are typically negligible. That looks too much like an R for my taste. But may become significant at smaller scales, meaning nano electromechanical systems. So they really don't mess up enough at the micro scale to cause that many issues. But as we continue to miniaturize things, they become more and more prevalent. No mathematical models or anything like that for this guy. All right. The last one that I want to talk about for today, and this is just because our air damping is a good 5 pages of notes just in and of itself, so we're going to leave a little bit early, is the mode conversion losses that I referenced a few moments ago. Okay. So for a resonator, ideally, only a single resonant mode will be excited. If other modes have a resonant frequency near the main resonance, they will also be excited. So if we think of something like a resonator that was based on a cantilever beam like structure, essentially we would want to make sure that it could only easily bend in one particular direction, right? So if like the width of the beam and the thickness of the beam are of comparable dimensions, then the beam can easily deflect both up and down and left to right, and that might be problematic, right? So we can get rid of a lot of mode conversion losses just by good design and making sure that our structure can only easily resonate in one particular direction. But if if those resonant frequencies are close enough together, we can see an overall reduction in the quality factor of the structure, right? So essentially what we would find is that the total quality factor due to mode conversion is going to look something like this, where we'd have A1 over Q1 plus A2 over Q2, et cetera, all the way to A sub n over Q sub n, where A sub I is the fraction of the total energy associated with each resonant mode. So if we had a resonator where our quality factor for one mode was 100,000 and 99.99%, excuse me, 99.9% of the vibrational energy was in this resonant mode 1. And we had a second vibrational mode whose quality factor is 100 and only 0.1% of the total vibrational energy is associated with that mode, then our total quality factor for this guy would actually be 0.999 over 100,000 plus 0.001 over 100. Take the reciprocal of this guy, and we wind up getting approximately 50,000. So 50,000, sorry, I got my decimals there. 0.013. So even having 0.1% of the vibrational energy leached into this second much lower vibrational mode, or much lower Q factor vibrational mode, causes a net decrease of the Q factor by effectively 1/2. Okay, so like I said a couple of minutes ago, this is where we're going to stop here because air damping is going to take such a long time to go through. It's essentially its own lecture. So we have roughly 30 minutes left of class if anybody wants to ask any further questions about their exam, etc.